Hi, I'm David, and I'm going to talk about learning preference constraints. Many things we might want an AI system to do can be naturally decomposed into rewards and constraints. For example, consider you have a self-driving car and you want it to drive you to the grocery store. While you might only explicitly specify the reward component of this task, there are a lot of implicit constraints, such as following driving rules or making sure the drive is comfortable. In our paper, we argue that it's beneficial to model this explicitly as a constraint problem. So we looked at this driving environment where we learn a policy to control the orange car, while the white car moves on a fixed trajectory. Each dot is one time step, and the red dot marks the middle of each trajectory. We can train a policy using a reward that has a positive term for driving close to a target velocity, and negative terms, for example, to avoid getting too close to other cars, among other things. We can also encode the same task as a constraint problem, where the reward only has the positive component, and the rest is encoded as a constraint function that has to stay below some threshold. So you need to stay at least some distance away from the closest other car and so on. Both approaches give reasonable behavior on this task. Next, we consider a different task. So instead of driving at a target velocity, we might want to pull over to the right side of the road. So we can try out to switch out the positive term in the reward without changing the penalties. But we find that then the car does not pull over because the penalty terms are not too large. Using the constraint formulation, on the other hand, we can just switch out the reward and get the desired behavior because the reward and the constraint are not directly traded off against each other. Here, in a third scenario, the street is now blocked by 3 cars. For this situation, it turns out the reward penalty is too small and the orange car tries to drive in between the others because it can still achieve a high reward this way. The constraint formulation does not have this problem because here the orange car needs to stay some distance from the closest other car and it stops. So overall, the constraint formulation turns out to be more robust in this situation. In practice, the reward or goal might be easy to specify, but the constraints are unknown. This motivates us to introduce the constraint linear best arm identification problem. It's a linear bandit problem with a set of arms that could correspond, for example, to the different controllers for the car in some feature space. And we have some known reward parameter theta. So in this picture, we know the reward gets larger along the y-axis. And we have a constraint parameter phi that separates the arms into a feasible and infeasible region, but phi is unknown. Instead, we can, in each iteration, only evaluate one arm and observe its constraint value under some noise model. So this means we have to estimate the constraint boundary from noisy data. Our goal is to find the best feasible arm as quickly as possible. So to solve this problem, we propose the Adaptive Constraint Learning algorithm. The key idea of this algorithm is to estimate the constraint boundary using confidence intervals. So here we might only know that the true constraint boundary is somewhere in between these 2 lines, but still, given this, we can determine a set of arms that's certainly feasible and a set of arms that's certainly infeasible. Additionally, we can look at which arm among the certainly feasible arms has the highest reward. So this is our current solution candidate, and we know that all arms that have a lower reward than this are certainly suboptimal. The remaining arms are the ones we're still uncertain about. The idea of the algorithm is now to select arms that will most reduce our uncertainty about these remaining arms. For example, here it might select this arm, which is inside the uncertain region. The algorithm would then observe that this arm is actually infeasible, and it can use this information to update the confidence bounds. This way, the set of uncertain arms will shrink until we can identify the correct optimal arm with high probability. In our paper, we provide a lower bound that's problem dependent on the number of samples that we need to solve any problem. And we also derive a sample complexity upper bound for adaptive constraint learning, which depends on the same problem-dependent quantities. So there's a small difference in the set that we maximize over, but you can see our paper for a detailed discussion. Finally, we try out our approach in simulation. So here we consider this driving simulation that I showed before. We use a binary observation model, so we only observe if the evaluated controller is feasible or not. And we want to evaluate how many samples we need until we can identify the best constraint controller. So lower number of samples indicates a better result. We compare adaptive constraint learning, our algorithm, to uncertainty sampling, which is a simpler active learning method, and uniform sampling as a baseline. Uncertainty sampling helps a little bit, but our approach performs even better because it adapts its strategy to focus on the most relevant arms for finding the optimum. To summarize, we argue that constraints are a particularly robust and natural way to represent human preferences, and we proposed adaptive constraint learning, which is a sample-efficient algorithm to learn about unknown linear constraints. If this is interesting to you, come to our poster at the in-person conference or read the full paper at this link. Thank you very much.